Hello, my name is Christoph Moll. I'm heading a research group in corporate technology at Siemens, and I want to give you an overview about the structure of Siemens, about the setting of the group, of the team, and about the application which we tackled in the last year, at least some of them. Let me start with a closer look on the Siemens structure today. So, Siemens is structured in 5 companies today. Smart infrastructure, focusing on all kind of topics around infrastructure, building technology, um, low voltage power grids, smart grids, other topics in the infrastructure area, digital industry, having a strong focus on production, product design in industry, digitalization of industry, simulation of simulation tool of products. Siemens Energy was everything around energy generation, so famous for gas turbines, wind turbine business, energy transportation, so high voltage line, and energy transformation, so everything from high voltage to low voltage. Then we have Siemens Mobility, so most of you might know Siemens from the high-speed trains, but we are also strong in the entire rail infrastructure topics and also on the car infrastructure side or car traffic infrastructure. We have a lot of software, traffic lights, software around that coming from Siemens. Siemens Energy, most of you might know that Siemens is building things like computer tomographs or magnetic resonance tomography, but there is also Siemens acquired some companies working in chemical laboratories, and recently we acquired a company working in cancer treatment. So there's a lot of strong footprint in everything which is around healthcare. So those 5 companies are supported by central services, one on finances, on buildings, on global business services, and by corporate development, which itself includes corporate technology. And that's the department I'm in. The corporate technology is providing technology for different areas for the entire companies. So in this sense, we are there that are our customers. So all the companies which are presented to you, including, I might add some former companies of Siemens, like Osram, has been carved out of Siemens, the C-Place, which has been carved out, I think, 8 years ago. So all this is more or less the field where my team is running project, bringing technology, mathematical optimization to those customers. So let me start to introduce or to tell you a little bit more about corporate technology, simply by explaining you the 11-digit abbreviation of my team. So my team is internally called CTRDABAMORD. So this means corporate technology, CT. So there we're talking about 2,000, around about 2,400 employees, 300 of them working in the IP department, the other mainly in research, some other functions like university cooperation aligned to that. Then one of these research departments is digitalization, research and digitalization and automation. So we are 500 researchers sorted in 7 technology fields. One of those technology fields is business analytics and monitoring. There we are 240 experts in analytics, so business analytics, learning, and other topics, and optimization, by the way. So we are located in 10 locations around the world in 8 countries. So you see that we are teams in Germany, in the US, in Austria, in Russia, Slovenia, in Russia, in China, in India. I forgot something. And we are grouped in 14 research groups, each one being localized in one country and representing a certain technology, having a certain technological focus. So, and my team has a focus on operational research. It's called Operational Research for Decision Support. So we are 14 members, all of them mathematics, most of them having a PhD in mathematics. All of them have strong IT skills, so we call them software developers. 2 of them are certified software. So what's the mission of this team? The mission of this team is actually to the design and the development of custom-tailored planning algorithms and software tools. And we don't do that. We do this for our internal customer, which I gave you in the first slide. So our goal is to come to a direct value creation either for our internal customer if they use it, or for their end customer. And the technology which we use is on one hand is mathematics, so nonlinear, mixed integer linear programming, graph theory, discrete combinatorial optimization, stochastic optimization. And everyone in the team has a strong software development competence. So our main product which we deliver is software including at least an algorithmic library or something like that. Typically, but it also goes until to solution or deployed service in the cloud or something like that. So to explain you a little bit what we do and how we do and what our role is, I'd like to take this picture. So if you start from the domain expert world, let's take a concrete example. We are discussing with someone who wants to improve the production planning in his factory at Siemens. So his domain is his production. He's an expert in production planning. He knows everything about his production and he knows his concern of his factory. So that's a domain experts world, the clear mindset. And so we are trying to understand what this is, to formalize it, to put it in a kind of formally define this. And once we have formally described that, we transfer this into a mathematical model. That's typically our job. Then we have to do something which is taking this model and feeding this, getting some data for concrete planning instance, and feeding that into an algorithm which solves the problem. Ideally, the algorithm finds the optimal solution. Now we have to interpret this mathematical solution in terms of the domain. So what does it mean? We have a corner of a polygon, if you want, or variable settings, values which belong to an optimal point, and we have to compute the plan out of that. So we're discussing with this domain expert. He doesn't want to know anything about polygons or variables. He's not interested in that. What he wants to see is a Gantt chart or something like that, so that he can have a look on this plan and answer to the question: is that something which you expected from an optimizer to be a plan? And typically, if you do this in the first round, you will find a lot of things which you have forgotten in your model, and so you do this iteratively, which means that you have to spend a lot of time in redoing this mathematical, changing the mathematical model, feeding this, trying this, doing the interpretation, and so this is more a process and something which you do once. That's why we invested a lot to do this part efficiently. So what we did, or first, obviously, let's start with a core most cases, if we have now mixed integer linear program in mind, which is a typical situation, then we are using at the core engine, we want to use FICO or IBM CPX, Groby or Skip, depending on some decision which we want to do later, but we are not implementing any mixed integer linear solver. So we want to use this. That's one part. So the solving the problem will be done by one of those solvers. So what we invested a lot into is to develop software tools which allow us that if we have a formal model described in an AMPL file, and on the other hand, we have some classes representing the domain experts world, then to generate the code which is doing this ugly interface handling. So what this code is doing at the end, it's opening a new problem, it's creating variables, it's creating constraints, it's populating this matrix of constraints and variables with parameters, reading out accessing some data from classes which represent the domain experts world. Then an optimization is happening somehow, and then we have this readout of the solution and transport into something like which is also in the domain experts world, so something like a plan. So we try to generate at least this part more or less automatically, given classes of the domain expert world, classes for the solution, and a selection of the solver, and a model which comes in an AMPL. So another tool which we use is that's more on the model building part. So this is MOAS and OptFace. So these are two tools which are there to support the model building process itself. You're building AMPL files, and you have an infrastructure which allows you to fast generate the entire optimizer. So you're skipping this part that you're coding the domain experts work. You're using other file formats to create first instances of that. And then you can do things like experiment checking out which solver works best for those kind of instances, which model works how fast. This is something which we can use to come up in an early stage of the project with a concrete estimate on how good optimization might support this project. Okay, to come up to final view of to finalize this part of the talk. So what our job is actually doing the interface to a given domain expert. So we are speaking to him. We have in the back of our mind in these discussions, obviously, we have something like a mathematical modeling brain, which is trying to guide us through this discussion with the domain experts. So at a certain point, the model is generated in the brain, put into a computer, an API file or something else. Then we use an infrastructure which helps us to build everything fast. So it's a cooperation about mathematical model building and business intelligence and intelligent usage of it. So and that's a claim. So good tool chain is and people used to use this tool chain is something which you need to do this efficiently. So you can create everything from scratch, but that will hardly be efficient. And one statement which is perhaps more interesting, if our internal discussion with our partner were more from the coming from the learning side, is to explain them what we are doing. So we always tell them we are not using data to point of truth that's coming from this discussion with the domain expert and the mathematician. That's what's building the model. So we are only using the data afterwards to check, to make runs, to check the model. So we don't use data to extract the model. We don't extract the model automatically. Okay, so far. Now let's jump into some applications. First one, this is a slide which actually gives you also a little bit of history of this team. So this team was founded in the middle of the 90s, and based on previous work with previous people who have worked on mathematical optimization for chip design. So also at the same time when Corto was working in Bonn on chip design, so there was in Siemens first people trying to solve mathematical problems chip design, and there was also some reasoning first time who tried to do logical validation on such circuits. That was a starting point of a team of people coming from both disciplines. Then came on the optimization part, a strong focus on things like phone networks. So there was a lot of graph theoretic algorithm. And in this case, you try to analyze the problem of digging costs. You want to minimize digging costs. So you want to build infrastructure for telephone cable networks, and now you want to dig those. You have to dig those cables to get telephone connection to every building. And giving such a plan of a city, you now can try to create to estimate the cost of a phone network and to give a first impression of the cost which you would have when if you install a phone network there. Then came a lot of this is then came a lot of with the mobile phones, new infrastructure, new technology, new problems for us. And so we did a lot of frequency assignment stuff, antenna positioning, all those kind of topics. Afterwards, we had a certain special case and special situation in Siemens. So Siemens wanted to enter the photovoltaic business, and they wanted to specialize on, let's say, special designed factories, so plants which are in complex three-dimensional locations, so location like you see on the picture, and there the engineering is complex. So you have a complex engineering step to position all the modules, and that's something which they had to do a lot of tenders. So we built a tool for them to reduce the time to answer to a tender. So simply given a certain three-dimensional structure, use certain rules which you have from the engineering, and come out with a position of the modules, come out at the end with something like that, with a bill of material, CAD layout of this, be able to answer to a tender. So finally, two other things coming from engineering. One was on truck layout, so we tried to automatically assign positions of certain things in a truck. So this looks like a three-dimensional problem. Actually, it's more one-dimensional problem because you are actually assigning certain object to certain fixtures on the trails. So you have a three-dimensional overlap, all kind of rules which you have to omit, and other things like you can't put something which needs to be cold near to something which is directly getting hot and things like that. Finally, something which was still a significant part of my team's working on is on power grids, and there we are doing the dispatching of the power grid. So dispatchers which control the batteries more or less, or diesel generators, so where the energy comes from. So the initial situation is that you have an estimation of the grid which you expect to get from photovoltaic, from the wind, from the renewables. You have an estimation of the consumption, and now you want to optimally dispatch your battery and your equipment. Yes, so far, why do I call it engineering? Because we use it in a simulation environment where you want to validate the equipment for such a grid. So you want to decide how much photovoltaic you need, how much wind you need, And so these dispatchers you want to execute it a lot of scenarios for a couple of years and run through all this. So this dispatcher need to decide very quickly, very often. So it's very small maps which have to be solved extremely fast. That's the technology behind it. Now let's jump to another, or at least we can take the microgrid as a first example. So where you want to optimize the performance of a machine. So other examples are actually magnetic resonance tomography. So here you have, if you want to generate good pictures, you need to generate pulses which have certain features, and that's something which you can formulate as a mathematical optimization problem. So which pulse you need to generate, which feature in the picture, something which you can try to optimize with mathematical models. One member of my team is working in this area. Now you have the other thing is that was what we had on this former company which left Siemens. There was a company which, or there is a company which is no longer Siemens, which is producing placement machines. And this placement process itself contains a lot of discrete decisions. So if you imagine there is this small thing which picks small things and puts them on the board and certain things. So we have something naturally small TSPs there, or vehicle routing problems if you want. And you have line balancing problems, and you need to divide the pieces which you want to place on this board. You need to subdivide this to the machines to have a similar load on such a line. And if you have tens or a lot of boards which you want to produce, then you need to put this orders in a certain sequence to minimize changeover time, the significant changeover time between two types of boards. And if you have tens of factory with a lot of such lines, then you can use mathematics to group your products and to assign your products optimally such lines. This is something which is material flow. There you are in the International Post Office. In this case, it's in London. This is a Moll project, and there we used linear programming based, I would say, a simulator to forecast the material flow within this factory. Last one is an actual project. You're looking in the back part of a CNC machine. So in the front end, what you see here is storage for tools. These are tools, and what is happening actually in this machine, some tool is working there, and once this work is completed, this device here will go there, take the tool, put it back in the storage, pick another tool, and bring it back there. And in the meantime, a third tool is actually completing or doing an operation. So you always have during one operation, you have here an exchange, bringing back the previous tool and getting the next tool to this position. You don't want the optimization problems actually, given the sequence of tools which you need and the processing time, how to organize your storage in such a way that you don't have any delays there where you have to wait for the tools. So let's go to the other example. So the other final example or set of examples applications are in the field which I gave you in the initial example when we discussed domain experts and things like that. So you're looking into a production of a factory. This first example is a former Siemens factory, Osram LED production. And there you have one thing, so this is a wafer which you see there on the wafer chips. So the first thing is when you produce such wafers, you can control this process, and the outcome of that is a wafer which contains a lot of chips with a lot of different qualities. So controlling this process in such a way that if you have 10 of those processes in parallel, that the entire set of wafers which you create represents more or less what you expect to be able to sell to your customer, is something which you can formulate, or which you formulate as an optimization problem and try to support Osram LED production with that. Another thing is once you have LEDs in storage, and on the other hand you have customer orders, you want to take certain wafers out of the storage, let's say 10 of them, and you want to assign them to customer orders. So on each wafer you have a subset, let's say 25 of them can be used for a certain customer, and so you need to find the other 75 to fulfill this order in other wafers. And so this gives you a problem where you have to select wafers, you have to assign them to orders, and at the end you want to minimize scrap in the factory. Okay, so far for that. So now I'm at the end of the application which I wanted to present today. If you have questions, and I'd be happy to answer to them, just join the session on the 25th September at 10 a.m. or at 9 p.m. Central European Time, obviously, and ask a question, please. Let me make a final statement. So I have 25 years of experience in doing this, so I might state that applying optimization in a real-world application can be fun, even in industry. I suppose that all of you are persuaded that it can make a lot of fun in university. So my name is Christoph Moll. I'm head of the research group Operational Research for Decision Support in Corporate Technology at Siemens. If you want to send me some feedback, information, have questions, you might send me an email to christoph.moll@siemens.com or join the session on the 25th of September. Thank you for your interest in this talk. Goodbye. Looking forward to meet you in the session.